All right, lesson 1.4. We are talking about inductive reasoning. So, little bell ringer here to start. Wants to know how does the number of regions change when another point is added? So, pause for a second. I'm going to count. This is the first term. This is the second term. This is the third. This is the fourth, so on and so forth. Okay. How many regions are in the first term? One. Second term.
Two.
Third term.
Three.
Four. Fourth term.
8.
How many terms would be in the fifth?
16.
How'd you know that?
Because
It doubles each time.
How do you know that?
Because just looking at it,
If you just
like,
look at it.
there's
Okay.
one,
How do I get from 1 to 2?
double it.
Double. How do I get from 2 to 4?
You double.
Double. 4 to 8.
You probably double.
Double. 8 to 16. Double. How would I get the sixth term?
Double.
Wait.
Double the 16th, right?
You guys find something.
So, here we had our terms. This is what's happening, this is how many are in each one. This is what is happening each time. Is there a pattern?
Yeah.
Yes.
Yes. Okay. So, starting off, we're going to be listing some vocab and defining. So, we're going to start with inductive reasoning. Does anyone know what inductive reasoning means? Okay, does anyone know what reasoning means?
Yes.
What's that mean?
Reasoning means to it's a tough word to define. It really is, but I do know what it means.
What are you doing when you're reasoning about something?
Agreeing.
You're explaining, or you're agreeing, or you're explaining why something works. Okay? So inductive reasoning, okay, is you are using patterns to solve problems. Another way to think about that is you are explaining what is happening. Okay. Another vocab term is going to be conjecture. Does anyone know what conjecture means? I don't know if you've heard it in math before, but you've probably heard it in science.
Nope.
Does anyone know what it means to make a conjecture?
It's like I don't know.
Anyone have a guess? A conjecture is a rule or pattern to a sequence. Okay, it's the rule or pattern to what is happening in the sequence. So if I took you back to the bell ringer that we had, what did we say was happening every time? Multiplying by 2. That would be our conjecture. Okay, our conjecture for that one would be multiplying by 2. Okay. So next vocab term is counterexample.
Counter what?
Counterexample. Does anyone know what counterexample means?
An example that counters.
Exactly. What does the counterpart mean?
It means, like, in
You
football
come back,
terms,
you come
it's like to fake. Like,
Right.
you're going
So
to misdirect.
counterexample is something or an example that proves it to be false. Okay, so a counterexample is an example that proves something to be false. For example, if I told you that any number is always positive, what's a counterexample you can give me?
Any
Negative.
numbers?
A negative.
Any negative number, right? If you said -2, that would be a counterexample because that's not positive. Okay? If I use the American flag, the only color on the American flag is red. What's a counterexample?
And right.
White, blue.
So a counterexample would be white or blue. Okay? So that's what a counterexample is. It's proving a statement to be false. Okay? 2 more terms here. Next one is talking about 2 different sequences. So we're going to talk about arithmetic sequences and geometric sequences. What is a sequence?
It's like
In order of
form
things.
events.
It's a form of events. It's an order of things, okay? We need to talk about the difference between arithmetic and geometric. Does anyone know what arithmetic is?
Math.
It is math,
Like
but
equations.
A curriculum.
it's numbers, okay?
Yes.
Arithmetic sequences uses numbers and operations. What do I mean by operations?
Like plus minus.
Exactly. And I can also include multiply and divide.
Yeah.
Okay, so those are the operations that can be used in arithmetic sequences. So on the bell ringer that we had, what operation did we use?
Multiplication.
Multiplication. Okay, so that was, we turned it into an arithmetic sequence. So if arithmetic sequences are numbers and operations, what is geometric?
Letters.
Shapes.
Shapes. Yeah, it's like pictures,
Shapes and colors.
pictures and figures.
I love coloring.
Okay, so this could be graphs, this could be drawings, this could be images, it can be anything. Okay, as long as there's no numbers. So on the bell ringer that we had when it had all those pictures, okay, that's geometric. Okay, because you're looking at pictures. However, what did we do with those pictures?
We made it into.
We made it into arithmetic sequence, right? So they kind of go hand in hand if you really want them to, okay? So first one I want to look at is this guy right here. So first of all, what kind of sequence is this?
And minus 6
Subtracting.
sequence.
It's what kind of sequence is it? Geometric or arithmetic?
Arithmetic.
Arithmetic. Yep. So how you're going to solve these, because I want you to find the pattern and tell me what the next two terms are. Okay, so you're going to start with the first. How do I get from the first term to the second term?
Subtract 6.
I'm subtracting 6. Can I assume all of these are subtract 6?
No.
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 Gotta check. How do I get from here to here?
Subtract 6.
Subtract 6.
Yep. Here to here.
Subtract 6.
Subtract 6.
Here to here.
Subtract 6.
Subtract 6.
No, this is.
Okay, so what would my conjecture be?
Subtracting 6.
Subtracting 6. Remember, conjecture means what the rule is. So we are subtracting 6. So how would I find my next term?
Subtract 6, probably.
To get
58.
58. And to get my next term,
52.
I would subtract 6 to get 52. Okay. What I want you to do in your groups, I want you to do example 1, A and B. Go. I want you to tell me what the conjecture is, and I want you to tell me what the next two terms are. Go.
So it's going down.
On part A, remember we start from the first term, go to the second term. What's happening?
You divide it by 2.
Okay, did anyone say anything different?
You could say.
Did anyone say subtract 400?
I guess
I multiplied by
you
0.5.
couldn't do.
Okay, I'm going to stick with this for now. I'm going to subtract 400. What's happening from 400 to 200?
You're subtracting 200.
Subtracting 200. What am I happening from here?
You're subtracting 100.
Yep. So what's happening in that conjecture?
You're dividing by 2.
Right. So the easier way to say this would probably be to divide by 2. Okay, but I want to tell you that both of those conjectures would work. Okay? Or someone said multiply by 1/2. That would work too. So what would my next two terms be if I continue to divide by 2?
50 and 25.
50 and 25. Okay? On part B, how do I go from 18 to 24? We need to add 6. How do I go from 24 to 32?
Add 8.
Add 8. How do we go from here to here?
Add 8.67. Oh, add 10.67.
Because what did this go to? 42.6 or so. So what do you think should have been added right here?
10?
You would think it'd be plus 10. Is that exactly what happened?
No.
No. So what do you think happened?
This is an improper equation.
It does not work. This is not a sequence. So it is okay to have sequences not work. So what that means is this would be a no solution. Okay, this sequence does not have a solution because there was no specific conjecture going on. Okay. Okay, so this is a geometric sequence. How do I know that?
It's
Because
dot,
it's not-
or
It's
shape.
got pictures. Okay. But what we noticed is that we can take geometric sequences and turn them into arithmetic sequences, which is what they did here. Okay, so let's solve it how we know arithmetically. So how do I get from 2 to 6? Add 4. How do I get from 6 to 12?
Add 6.
Add 6, 12 to 20.
Add 8.
Add 8. What would I do next?
Add 10.
Add 10 to get
30.
30. Okay? So we could do it arithmetically that way. But I want to challenge you to do it geometrically. Is it easy to go from the first term to the second term? What I'm asking, like this could be here, it could be here, it could be here. Do you see that? Okay, so what I'm going to advise you, and if you want to write this little note down, I want you with geometric sequences to compare the second and the third term. That'll make it a little easier. Compare the second and the third term. In your groups, I want you to talk geometrically what's happening every single time we move. What's happening? What's happening? We're going to compare the second term and the third term. So here's my second term. I want to find that in the third term. That can be right here. What happened then? What did they add?
We're adding a row and a column.
Bingo. So your rule or your conjecture for this one would be added a row and a column. Okay, and then if I checked for the second one, or the next one over, there's that one, there's that one. Did we do it again? Did we add a row and a column?
Yes.
Yes. Okay, so that would be, this right here would be your geometric reasoning. This would be your arithmetic reasoning or your conjecture. Okay? What I want you to do in your group is I want you to look at this one together. I want you to give a geometric reasoning and I want you to do an arithmetic reasoning. Go. How many of you are more comfortable with the arithmetic one? Using numbers. Okay, that one's probably the easiest one. Okay, so let's go to that to help us a little bit. How many dots are in term 1? 1, 2, 5, 3.
8, 9, 11.
Got there. 11, 14. Sorry, 4. Holy moly. Okay, so what's happening between 1 and 5?
It's just plus
Adding 4. Can we assume all of these are add 4?
No.
No, what's happening between 5 and 11?
Add 6.
6, 11, and 19.
Add
8. What would we do next?
You'd add 10.
Add 10 to get
29.
29. So your conjecture for the arithmetic version would be this. Okay. How do we figure it out geometrically?
So,
I'm going to ask you this. What terms do we look at to help?
Oh.
Like, do we look at the first term compared to the
Three,
second?
you always look at 3 and 4.
Always look at 2 and 3.
Wait.
Always start there. Look at 2 and 3 first. So here is my 2. I'm going to go find it in the third one. Here it is. What happened?
We added a row, a column, and a dot.
Added a row, specifically, added a row and a column. Specifically, where's the dot at?
Above.
Top.
And a dot at the top.
Could we call that a roof, technically? And we added a part of the roof.
Wait,
A roof and wall.
do you have to list, like,
What about the floor? We got
And a floor.
Yep, for your geometric reasoning, you want to be as efficient as possible, okay, and as specific as you can. Okay, so added a row and a column and a dot at the top. Okay, and then if I tried to find this in my fourth picture, here it is right here. Did we do the same thing?
Yes.
Yes. Sometimes you will see your sequences in a table. Okay, what I want you to understand in this table in your notes is that the year, those are technically the terms we're comparing. Okay, and then the club members, that's the number of each term. So for these, to find our conjecture, are we comparing the year or are we comparing the club members?
Club members.
Club members. So what's happening between 10 and 13?
Plus
Plusing 3. I think adding 3.
Add 3. How do we get from 13 to 17?
is 4.
Add 4. 17 to 22.
You'd add 5.
Add 5. So what would my next one be to find it?
You'd probably add 6.
I would have to add 6. What's 22 plus 6?
28.
28.
So smart.
Okay, so sometimes you will have your sequences in a table. Okay. We are going to go into counterexamples. Again, what does a counterexample mean?
A false, like, example.
Proving something to be false. So again, my American flag example. I said the only color on the American flag is red. What's a counterexample?
No, it's blue.
There's blue or there's white. Okay, those are all counterexamples. So on your example 4, it says, what is a counterexample? So it's telling you there for sure is a counterexample. Okay, to show that the statement, the sum of two composite numbers must be a composite number, is false. So let's review some vocab terms here. What does the word sum mean?
Addition.
Addition. Awesome. Does anyone know what the word composite means? A composite number. Let's start with this. What's a prime number?
Oh, isn't it like
It's a
one,
number that
two?
can't be multiplied by anything other than
1 second.
Right, so for example, 5 would be a prime number, right?
Yeah.
Because it can only go in, or 1 and 5 are the only ones that go into it. Another example of a prime number would be 11, because the only numbers that go into it are 1 and 11. So a composite number is any number that's not prime. Okay, so a composite number would be like 12. What numbers go into 12?
6 and 2.
6 and 2. Okay, give me another composite number.
42.
6.
42. What numbers go into 42?
67. See what I did there?
Does work.
See what I did there?
Okay, so what we're trying to do to find a counterexample. So the statement is the sum of two composite numbers must be a composite number. How do we prove it to be false? So what this is saying, composite plus composite must equal composite. How do we prove this statement to be false?
Counterexample.
I know, how do we prove it to be false? What are we looking for?
A number that is false. That is not a composite number.
Right, so two composite numbers to give us a
Prime.
prime number. This is what we are looking for to prove a counterexample. Go try and find one.
I think every single one does.
Go try and find one, go.
Okay, 5.
So, give me your two composite numbers that you had.
8 and 9.
8 and 9. So if I do
the same number twice.
8 plus 9, what does that give you?
17.
17. So recap. Do you agree both of these are composite numbers? Yes.
Wait.
Is 17 a prime number?
Wait a second.
Down
Yes.
to Montana.
So this would work. Go try and find another example. I want each group to find one more. Go.
What if we do 10?
What you got?
Hey, found one. 10 plus 9.
What?
18 plus 9.
18 plus 9. I agree they're both composite. What's the answer?
27.
27.
Is that work?
3 is
Right. 27 is not a prime number. So this one would not work.
Owen! No, Owen!
Max. Owen.
9 plus 10. 19.
So if we do 9 plus 10, that would also work. That would give us
21.
19. So that one would work. Good. Max.
So my group got 42 and 25.
42 plus 25. Those would both work. What's the answer?
67.
That would work. I want two more. Yeah. 21 plus 8. I agree. What did they add up to? 29. Good. Hey. I want one more. Rosalie. I agree. 9 plus 4 gives you 13. Yep, that's okay. What I want you to notice, okay, even with these counter examples, you should be able to see a pattern. What is a pattern that you see in between all of those different examples?
9.
We are all composites.
Other than that.
Oh, I don't know.
A lot of them.
They're all red. All equal and odd numbers.
No,
They
that's-
do, okay, they do all equal an odd number. That is true. Okay, so we found what's common on the right side. What about the left side?
I don't know. Oh,
Also all composites.
that two composite like two of the exact same composite numbers can't equal a prime number.
True, Andy?
It's an odd and an even.
Bingo. You're adding an odd and an even number every single time. Why can you not add two even numbers together to get a prime number?
Even number.
Divisible by 2. Exactly. So it has to be one odd, one even. Okay? All right. One more thing that I need notes on. Okay? To prove something. Just write counterexample. Counterexamples.
On the side.
Yep. Counterexamples. So if I want to prove something to be true, comma, I want you to show me at least 3 examples that are true. So if you think something's true, you need to show me 3 examples that prove to be true. Okay? To prove something to be false. Yep, so to prove something to be false, that would be where the counterexample comes in. Okay, you only need to show me one example. Okay, show me one example that proves a statement to be false. Because if you already tell me that a statement's false, do you need to keep proving that to me, or is one example enough? Okay, if you're trying to prove me something to be true, Okay, if you just tell me one thing, can I still question if other things would work?
Yeah.
Yes, so that's why I need more for the true. Okay? So that brings us to example 5, and I'll get started. Example 5 here on A, the directions say for each conjecture, you're trying to prove it to be true or to be false. Okay, using what we just talked about. So on part A, it says for every integer, what's an integer?
It's a number that can go negative and positive.
Yeah, an integer is a positive or negative number, whole number, no fractions. Positive or negative number. You're trying to say for every integer n, the value of n squared is positive. So you're either going to try to prove that to be true or false. Go. Okay, so for part A, someone give me a value that they tested. Yeah.
I put 2 times 2.
Okay, so if I test n equals 2, and I'm plugging that into n squared, I get 2 squared, which is 4. Is that positive? Yes. Someone give me another one.
-8.
-8. So if I try n equals -8, plugging that into n squared, I get -8 squared, which is
64.
Yep. Someone give me another one. Aiden.
-3.
If I try n equals -3, I get n squared equals -3 squared equals 9. Are these all true? Yes. So, what is our statement then? Statement is true. If you do 3 examples, okay, could there still be a counterexample that you might have missed? Yes. Okay. Why is this never going to be false though?
Negative is positive.
Negative times a negative is a positive. Any number that you plug into that equation is always going to come out positive. Okay. So overall, that statement A is true. Okay. I am going to get you started on part B. Part B says for a number that is divisible by 4, the last 2 digits are divisible by 4. So what that means is let's all try the value 184. Okay, I'm going to explain what this is saying. It is saying the last 2 digits are divisible by 4. Is 8 divisible by 4?
Yes.
Is 4 divisible by 4?
Yes.
Yes, so the conjecture is saying if that's true, then this whole number has to be divisible by 4. Test it. Is it true? Can I take 184 divided by 4?
Yes.
What'd you get?
122.
1?
46.
There we go, 46. So this held to be true. Go find 2 more examples. Go try 2 more numbers. What did you guys come up with after going through examples? Is it true or false?
True.
This is true. Yep, you would go through and show me 2 more examples, but to save time, I'm going to not do that today. Okay?
I spelled true.
Again, something you have to be careful about. Even though you get 3 true statements, could there still be a counterexample somewhere? Yes, okay, you really have to think about these a little bit. All right. Number 4, how do we find a pattern? What do we ask ourselves?
What is different between the first and second?
Yep, how do you go from 4 to 11?
Add 7.
Plus 7.
Add 7, 11 to 18.
Plus 7.
Add 7, can I assume all these are add 7?
Yeah.
Make sure you check all of them to be sure. What's 18 to 25? Add 7. So our conjecture is what?
Plus 7.
Adding 7. So what's my next term?
32.
32. What would my next term be?
39.
39. Awesome. Clap once if you agree with all that. Bingo. Number 5. How many of you kept it geometric? How many of you turned it into numbers? Kind of mixed or both? Okay. I'm going to turn it into numbers. So how many regions are in the first one? 2. Second? 4. Next one? 6. 8. So are we comparing these numbers?
No.
What are we comparing?
Bottom.
Yep. So what happens from 2 to 4? Okay. Can we say this doubles? No. So what's better to say?
Plus 2 plus 2.
Yep. Add 2. Add 2. Add 2. So what's happening for the next one? To get? It'd be 10. Clap once if you agree with that. All right. Number 6. I heard some not arguing, but some people weren't agreeing. Okay. Someone give me a value to test through this. N equals, Colin.
9.
N equals 9. So if I plug that into here, I get 9 squared plus 1. What's 9 squared?
81.
81 plus 1 is
82.
82, which,
It's not on.
yeah, so this would be a counter example. So, what's the answer? It is false. Do I need to prove another one? No. So, some of you that did get 3 true ones, remember, there are sometimes still those counter examples. Okay, you got to think about it. Questions?